Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just imagine for a second, looking up at the night sky.
Yeah.
And realizing that the vast, vast majority of what actually dictates the movement of all those stars, it's completely invisible to us.
It's a wild thought.
It really is. I mean, for over 50 years, the absolute brightest minds in theoretical physics have basically been hunting for ghosts.
Literal ghosts in the math, yeah.
Right. They've built these multi-billion-dollar subterranean detectors, burying them deep inside abandoned gold mines just to shield them from cosmic rays.
Smashing protons together at the Large Hadron Collider.
Exactly. Smashing things at nearly the speed of light. And all of this unprecedented global scientific effort is just to find these invisible particles that supposedly make up, 85% of the mass in the universe?
85%, yes.
And what have they actually found after all this time?
Absolutely nothing.
Zero particles.
Not a single one.
For decades, our entire understanding of the cosmos has just leaned on these two colossal phantoms, right? Dark matter, to explain why galaxies don't just fly apart when they spin, and dark energy, to explain why the expansion of the universe is accelerating.
And while the standard model of cosmology is brilliant in a lot of ways, I don't want to dismiss it, but it does place us in this deeply uncomfortable position.
Of not knowing what our universe is actually made of.
Right. We're basically admitting that we have zero idea what 95% of reality actually is.
Which is terrifying.
It is. I mean, we observe the gravitational shadows of these entities. We see the effects they supposedly have on the matter we can actually see.
Like stars and gas clouds.
Exactly. But the dark entities themselves, entirely theoretical. We've built our most advanced models on the assumption that the universe is just full of stuff we can't see, touch, or interact with.
But what if, and this is the core of what we're getting into today, what if the reason we haven't found dark matter isn't because our detectors are bad?
Right.
What if the problem isn't the universe at all, but the actual mathematical lens we're using to view it?
That is the million-dollar question.
Because today we are exploring this truly radical new mathematical approach. It was recently published in the journal Physica Scripta.
Yeah, it's a fascinating piece of work.
And it proposes something profoundly disruptive.
Yeah.
The premise is basically, we haven't been failing to find dark matter. We've just been doing the math wrong.
We've been taking shortcuts.
Right. So this framework is called the Alena Tensor.
Mm.
And it was developed by a Polish researcher, Piotr Ogonowski.
Yes.
And it offers this unified, rigorous method to describe physical systems across everything. I mean, curved spacetime, slat spacetime, classical mechanics, even quantum theory.
It is an incredibly sweeping proposition. I mean, to really grasp the sheer magnitude of what the Alena Tensor is attempting to do here, we really have to dissect how physics models the universe right now.
Okay, lay it out for us.
Well, we have to talk about why the current model historically requires so many approximations. Specifically, there's this glaring oversimplification in modern cosmology that we call the dust problem.
The dust problem. Okay, let's unpack this. Because I know that when physicists sit down to solve Einstein's field equations, they have to make some serious compromises.
They do. The math is notoriously nonlinear.
Right. It's punishingly complex.
Yeah.
But when you say cosmologists rely on an approximation called dust, what exactly are we talking about? Because obviously we know the universe isn't filled with, actual household dust bunnies.
No, definitely not household dust. In cosmology, specifically in models like the Friedmann-Lemaitre-Robertson-Walker metric.
Oh, that's a mouthful.
Right, FLRW for short. It's the absolute foundation of Big Bang cosmology. And in that model, dust is a very specific mathematical term.
Okay. What does it mean mathematically?
It means treating all the matter in the universe, stars, gas clouds, even entire galaxies, as idealized, non-interacting point masses.
Wait, non-interacting?
Yep. It assumes these points of mass exert gravity, sure, but they have zero internal pressure.
Really? Zero?
Zero. They don't push against each other. They have absolutely no internal friction.
That seems crazy.
It's a massive mathematical convenience. Their complex internal rotational dynamics, the sheer stresses inside their structures, all of that is basically just smoothed over or totally ignored on a microscopic scale.
Wait, I'm struggling to visualize why anyone would do that. If we know that galaxies are these violent swirling storms of plasma and billions of stars, why would physicists ever agree to model them as static, non-interacting points?
Because Einstein's equations are practically impossible to solve otherwise.
Oh, I see.
Yeah. And to be fair, standard physics does account for rotation in a localized way.
Right, because we've known galaxies spin since, what, the 1920s? Hubble figured that out.
Exactly. But they usually calculate it using perturbations. So when astrophysicists look at a spinning galaxy, they calculate the mass of the visible stars in gas. They measure how fast it's rotating, and then bam.
They hit a massive discrepancy.
A huge one. The visible mass just does not generate enough gravitational pull to keep those really fast-moving outer stars from just flying off into deep space.
Right. They should just be slung off like mud off a tire.
Exactly. So the traditional fix, the Band-Aid, is to inject this massive invisible spherical halo of dark matter around the galaxy to provide extra gravitational glue.
Just to make the math work.
Basically, yes. But the Alena Tensor looks at this and forcefully argues that you cannot just model the universe as static dust and then patch your errors with invisible particles.
Okay, so what does the Alena Tensor do differently?
It extends the mathematical solutions to general matter distributions.
Meaning what, exactly?
Meaning it forces the Einstein field equations to explicitly account for how matter flows, how it rotates, how it exerts pressure against itself, and how it generates internal friction and shear stresses.
Okay, I have an analogy for this. It sounds like we've been trying to understand ocean currents, all the complex global dynamics of the ocean, by only looking at a single drop of water suspended in a vacuum.
That is a perfect analogy.
Like the dust model just completely ignores the friction and the flow. If you only look at that isolated drop, you completely miss the tidal forces, right? You miss the temperature gradients.
You miss the massive kinetic energy of the ocean acting as an entire unified moving system.
Exactly. Real physical systems in our universe are not made of idealized point masses.
Galaxies are essentially fluids.
Yes. They are massive, interconnected, fluid-like structures. Matter flows in them. Energy transports dynamically from that super-dense inner core all the way out to the diffuse outer arms.
So there's constant movement and stress.
Constant. Internal stresses, vortical swirling motions, they appear naturally all the time. And the Alena Tensor actually proves mathematically that when you incorporate all these fluid effects, the friction, the momentum, the geometry of space-time warps in ways that dust models fundamentally miss.
Wait, so what you're saying is that the geometry of space-time isn't just reacting to the sheer weight of the stars.
It's not.
It's actually reacting to the complex architecture of how those stars are moving together. Precisely. In general relativity, gravity isn't just caused by mass alone. It's caused by something called the stress energy tensor.
Which is what?
It's a mathematical matrix. It describes the density and flux of energy and momentum in space-time. Mass is just one single component of that matrix.
Oh, wow. What are the other components?
Momentum, pressure, and shear stress.
But because of the dust approximation, cosmologists just ignored those.
They vastly undercalculated them. They heavily weighted the mass component and basically ignored the complex kinetic components, the off-diagonal terms of the matrix.
And the Alena Tensor brings them back.
It restores them to their rightful dominant place in the equations. And here's the kicker. When you actually account for the gravitational weight of this dynamic flow, the need for a dark, invisible glue holding the galaxies together, it suddenly vanishes.
Are you serious? It just disappears.
Poof! The structure of the movement itself creates the necessary gravitational effects to hold the galaxy together.
I mean, think about the philosophical implications of that.
They're massive.
If this holds true, we literally invented an invisible substance that makes up over a quarter of the entire universe, just to balance our mathematical checkbook.
Yeah.
All because we were using a simplified equation that treated a violent swirling galaxy like a bag of static marbles.
It's a profound paradigm shift. We go from a universe dominated by unseen, untouchable entities to a universe where the visible dynamics contain all the information we need.
It changes our entire relationship with reality. We aren't floating in this dark void filled with ghost particles. We're part of this incredibly intricate dance of kinetic energy.
Beautifully put. But to really cement how this physically works, we need to move from that abstract idea of flow to the concrete mechanics of rotation. We need to look at the observable behavior of spiral galaxies.
Right, because standard cosmology puts every single galaxy inside a massive dark matter halo.
Yes, to explain the flat rotation curves.
Okay, for you listening, just a quick refresher. In a standard orbital system like our solar system, the planets closest to the sun move the fastest, like Mercury. And the ones furthest away, like Neptune, move the slowest because the gravitational grip gets weaker the further out you go. But galaxies, they don't do that at all.
They absolutely do not. When astronomers, most notably Vera Rubin back in the 1970s, actually measured the rotational speeds of stars and spiral galaxies, they found something shocking.
A flat curve.
Right. The stars at the very outer edges of the galaxy were orbiting almost exactly as fast as the stars near the dense, bright center. The curve was totally flat.
Which breaks Newton's laws if you only look at visible mass.
Completely. According to strict Newtonian dynamics, those outer stars are moving so fast that the galaxy's visible gravity shouldn't be able to hold them.
They should just fly away.
So the dark matter halo was proposed as this massive invisible net of extra gravity.
But if the Alena tensor takes away that invisible net, what's tethering those stars? What is the alternative mechanism here?
The mechanism is the organized rotational transport of angular momentum.
Okay, break that down for me.
Under the Alena tensor framework, you don't look at an outer star as some isolated object trying to escape the center.
You look at the whole thing.
Right. You view the entire galactic disk as a continuous, coupled system. As the galaxy spins, angular momentum isn't just held statically by individual stars. It's continuously transported outward through the disk.
Through the fluid-like interactions of the gas and plasma.
Exactly.
Okay, but transport of angular momentum, I want to make sure I'm really grasping a physical mechanism here, because standard physics always uses that ice skater analogy, right?
Right. The skater pulling her arms in to spin faster.
Yeah. But a galaxy isn't a solid object like an ice skater. It doesn't have literal arms to pull in. It's mostly empty space. So how exactly is this momentum flowing outward?
It's transported through internal shear stresses and gravitational coupling.
Even across empty space?
Well, it's not truly empty. Those points of starlight are embedded in a massive medium of interstellar gas, plasma, magnetic fields. Plus, the stars gravitationally interact with each other in this continuous chain.
Oh, I see. Like a relay race of gravity?
Sort of. When the dense inner region rotates, it exerts a gravitational drag on the region just outside it. And that region drags the next one all the way to the edge. This continuous transfer of kinetic energy is a massive, organized flow.
Okay, here's where it gets really interesting.
Yeah.
You mentioned the stress-energy tensor earlier.
Yeah.
If mass creates gravity and energy creates gravity, are we saying that this literal flow of momentum, this invisible river of kinetic energy pushing outward, actually possesses its own gravitational weight?
That is precisely what general relativity dictates.
Wait.
Yes, and it's exactly what the Alena tensor rigorously quantifies. The actual flux of angular momentum contributes significantly to the local gravitational field.
Mind blown.
The framework proves mathematically that the faster and more organized the rotation is, the stronger this self-generated gravity becomes at the outer edges.
So movement literally mimics mass.
Perfectly. It mimics mass so well that it creates the exact flat rotation curve we observe. No invisible halo required. The kinetic architecture of the spin itself is generating that extra pull.
Okay, let me push back on this, though.
Go for it.
If movement mimics mass and angular momentum generates extra gravity, why don't we see this effect in our own solar system? Jupiter is huge. It has a tremendous amount of angular momentum. Why do we only need the Alena tensor when we look at an entire galaxy?
That is a fantastic question, and it comes down to the distribution of mass.
Distribution, how so?
In our solar system, 99.8% of the total mass is concentrated in one incredibly dense point, the sun.
Right.
The planets are just tiny specks orbiting that massive center. When a system is heavily dominated by a single central point mass, classical Newtonian approximations work perfectly.
So the flow doesn't matter as much.
Right. The kinetic off-diagonal components are negligible, but a galaxy is fundamentally different. A galaxy does not have 99% of its mass sitting in the central black hole.
It's spread out over tens of thousands of light years.
Exactly. The mass is distributed continuously across a massive disk. And because it's distributed, those fluid-like internal interactions and shear stresses become the dominant gravitational factors. The Alena tensor accounts for that exact scale-dependent transition.
From point mass to continuous fluid. That is staggering. It completely flips the script. We thought we were looking at the gravity of invisible stuff, but we were actually looking at the gravitational weight of movement itself.
It's a profound realization.
It's like we couldn't see the wind, so we assumed the trees were bending because invisible giants were pushing them.
I love that. Yes.
But, math is just math until it hits reality.
Yeah.
We have decades of high-precision telescope data on galaxies. How does the Alena Tensor actually hold up against real observational data?
This is exactly where it steps out of the theoretical realm and into the brutal arena of empirical data. Because you're right, a theory is useless if it can't match reality.
So has it been tested?
Yes. The framework has been directly tested against the rotation curves of more than 100 galaxies.
Wow, 100.
Over 100. And crucially, it wasn't just tested in a vacuum. It was put head-to-head against another very famous alternative to dark matter.
Oh, MOND.
Exactly, MOND, modified Newtonian dynamics.
We should definitely explain MOND for the listener, because it's kind of been the reigning underdog in astrophysics since the 80s.
It has. So MOND was proposed by Mordechai Milgram in 1983. And it basically suggests that we don't need dark matter at all if we just accept that Isaac Newton's laws of gravity break down at extremely low accelerations.
Okay, so like at the very edges of galaxies.
Right. In our solar system, gravity is strong, Newton works perfectly, but at the extreme outer edges of a galaxy where acceleration drops below this tiny specific threshold, which Milgram called a zero, MOND, proposes that gravity stops weakening as fast.
So MOND is essentially a mathematical tweak.
Yes.
It just injects a new universal constant to force the mass to match what the telescopes see.
It's a phenomenological theory. It was literally reverse engineered to fit the rotation curves. And, to its credit, MOND is incredibly successful at predicting individual galaxy curves.
But it struggles elsewhere.
Massively. It fails when you look at larger scales like massive galaxy clusters or the cosmic microwave background radiation. But the Alena Tensor is not a tweak like MOND.
Because it uses standard general relativity.
Exactly. It doesn't introduce any arbitrary constants like a zero. It doesn't modify Newton or Einstein. It just applies the generalized field equations without the dust approximation.
So how did the duel play out? When you pit MOND against the purely kinetic framework of the Alena Tensor on over 100 real galaxies, what did the data say?
The results are highly compelling, especially for a theory this new. In preliminary approximations, the Alena Tensor produces better, or at least comparable, fits to the curves compared to MOND in 80% of the tested cases.
Wait, 80%?
80%.
Without inventing a new universal constant?
Zero new constants. And that is using preliminary mathematical approximations, meaning there is still vast room for it to get even more accurate as the math is developed further.
That is insane. It achieves what MOND achieves, but from first principles, without tweaking gravity or inventing dark matter particles.
Exactly.
This raises a really important question, though. What happens to the physics community if a 3-year-old mathematical tool just starts consistently outperforming models that people have spent their entire careers building?
It's a painful process.
I mean, billions of dollars have gone into dark matter. MOND has been debated since 1983. How does scientific consensus even begin to shift when a new competitor steps in and immediately scores an 80% win rate?
Well, historically, consensus shifts incredibly slowly, and usually with massive institutional resistance.
Right.
Thomas Kuhn wrote about this in The Structure of Scientific Revolutions. You don't just abandon a prevailing paradigm because a new, elegant equation shows up. The old guard will defend the standard model fiercely.
And they kind of have to, right?
Absolutely. The dark matter paradigm hasn't survived this long by being useless. It solves a lot of complex problems, especially regarding how galaxies formed right after the Big Bang.
So to dethrone it, you need more than just a good fit on a graph.
You need undeniable proof.
Right, because fitting a curve isn't enough to overthrow 50 years of physics. If a theorist works hard enough, they can force-fit math to match an observation. What is the undeniable proof we're looking for? What's the smoking gun?
Well, you've hit on exactly how science advances. Theories are only scientifically valuable if they risk being totally wrong.
Yes.
A theory has to make a unique prediction, something the competing theories say is absolutely impossible. And the Alena Tensor makes a very bold, highly specific prediction about gravitational lensing.
Okay, the litmus test of lensing. This is crucial.
Yeah.
Let's establish how lensing works in the standard dark matter model first, so we can see the difference.
Sure. So gravitational lensing is one of the most spectacular consequences of Einstein's relativity. Massive objects, like a galaxy, have so much mass they literally warp the fabric of space-time around them.
Like a bowling ball on a trampoline.
Exactly. So when light from something further away, like a quasar far behind the galaxy, travels past, the light follows that curve. The foreground galaxy acts like a giant cosmic magnifying glass, bending and distorting the background light.
Which is why when we look at those amazing James Webb Deep Field images, we see those crazy, smeared, stretched out arcs of light.
Yes, that's distant light being bent through a funhouse mirror of gravity. Now, in the standard dark matter model, that visible spiral galaxy is sitting dead center inside a massive spherical halo of dark matter.
A giant invisible sphere.
Right. And because it's spherical, its gravitational pull is pretty uniform in all directions, so the way it bends the background light should be largely symmetric.
Regardless of the angle we're looking at it from Earth.
Exactly. It shouldn't matter. But the Alena tensor throws the spherical halo out completely.
It relies entirely on the rotational spin and the flat, pancake-like structure of the galaxy disk itself.
Precisely. The Alena tensor generates that pull based on the rotational dynamics and how momentum is transported along the plane of the disk. And because a disk is highly directional, it's flat. The space-time warping isn't spherical.
So it predicts an inclination-dependent lensing signature.
Exactly.
To make this incredibly tangible for everyone. If we point our telescope at a galaxy and we're looking at it perfectly face-on, like looking down at a spinning dinner plate, the background light will bend fundamentally differently than if we look at it edge-on, like the thin side of a frisbee.
That is exactly the prediction. The gravitational lensing will vary based on the inclination angle. Standard dark matter wouldn't care. A sphere is a sphere from any angle.
But the Alena tensor completely relies on that angle.
Because the extra gravity is born directly from the directional geometry of the spin.
That is a brilliant test. It's totally binary. It either happens or it doesn't.
Exactly.
If it happens, dark matter halos are in serious trouble. How soon can we actually test this?
We are actually entering the perfect era for it. With next-generation telescopes like the ESA's Euclid mission and NASA's Nancy Grace Roman Space Telescope, we'll be able to map the lensing effects of millions of galaxies.
With crazy precision.
Yes. We can categorize hundreds of thousands of galaxies by their inclination angle and analyze the signatures. If we see that distinct inclination-dependent signature, it would be a fatal distinction from the halo models.
It would be the exact smoking gun we need.
It would prove gravity is tied to the kinetic orientation of the galaxy.
Okay, so we have a mathematical framework that solves dark matter at the galactic scale.
Yeah.
And it offers a testable prediction. But we can't talk about the dark sector without talking about the massive elephant in the room.
Dark energy.
Exactly. If dark matter is the invisible gravity pulling things together, dark energy is the invisible anti-gravity ripping the universe apart. Can the Alena tensor handle dark energy?
It handles it by doing what it does best, rejecting arbitrary patches.
I love that. How so?
To understand it, we have to look back at Einstein's original field equations, specifically the cosmological constant.
Einstein's famous blunder. Let's walk through that because it's such a great example of physics forcing an answer.
Right. When Einstein first formulated relativity in 1915, the math predicted a dynamic universe. It had to be expanding or collapsing.
But the scientific dogma at the time was that the universe was static.
Eternal and unchanging. So Einstein essentially invented a fudge factor to stop his universe from moving. He added a term denoted by the Greek letter lambda, the cosmological constant.
It acted like a repulsive force to perfectly balance gravity.
Yes. But then a decade later, Edwin Hubble proved the universe was actually expanding, so Einstein called it his greatest blunder and took lambda out.
But the story doesn't end there, because in the late 90s, astronomers measuring supernovae discovered the expansion wasn't just happening. It was accelerating.
Something was actively pushing space-time outward faster and faster.
So suddenly, the cosmological constant comes back from the dead.
They resurrected lambda and plugged it back in to represent dark energy, the constant energy density of empty space, vacuum energy.
But wait, when quantum physicists try to calculate how much energy is actually in the vacuum of space, their answer is, well, it's completely wrong, right?
Wrong is an understatement. It's widely considered the worst theoretical prediction in the history of physics. The quantum calculation for vacuum energy is roughly 120 orders of magnitude larger than the observed value of dark energy.
That is absurd.
It's an absurd discrepancy. Even today, treating dark energy as a cosmological constant feels like a poorly understood patch.
It's just added to make the math work.
Exactly. But the Alena tensor takes a totally different route. Instead of an unexplained patch, dark energy emerges spontaneously from the Alena field equations as something called a field invariant.
Okay, so what does this all mean? What is a field invariant, and how does it act like dark energy?
In math, an invariant is a fundamental property of a system that remains totally unchanged regardless of your perspective or coordinate system.
Like the speed of light.
Exactly. Or the rest mass of an electron.
Yeah.
By showing that this behavior we call dark energy emerges naturally as a field invariant, the Alena tensor is making a profound statement.
Which is?
That this outward push isn't some new mysterious substance filling the void. It is a fundamental, inescapable, built-in property of the geometrical structure of spacetime itself.
Okay, I have an analogy for this too.
Let's hear it.
It's the difference between patching a leaky roof with duct tape, because you have no idea why water is on your ceiling. That's the standard cosmological constant.
Right.
Versus getting the architectural blueprints, looking at the structure, and realizing the leak isn't a flaw at all. It's actually a built-in, highly engineered irrigation system for a roof garden.
I like that.
It's supposed to be there. The water is the field invariant, and the complex piping is the geometry of the Alena tensor. It's a feature, not a bug.
Exactly. If we connect this to the bigger picture, it gives dark energy a profoundly deeper geometric meaning. It's not an arbitrary push anymore. It's a structural consequence of how space-time and energy fields are woven together. The geometry demands an outward pressure.
That is so elegant. But does this field invariant actually match the exact rate of acceleration we measure with our telescopes?
That is the open, rigorous question right now. The framework establishes the geometric basis, but physicists still need to see if it fully reproduces the exact rates of cosmic expansion over billions of years.
And the perturbations in the cosmic microwave background.
Right. The claim isn't that all of cosmology is suddenly flawlessly solved. The claim is that it offers a new geometric interpretation that changes the questions we're asking. We start asking, what invisible particle is pushing the universe apart? And start asking, how does the invariant geometry of space-time necessitate expansion?
It's just mind-blowing to apply this kind of dynamic math to the macro universe. But the ambition of this tensor doesn't stop at the edges of the universe, does it?
No, it does not.
Because to truly unify physics, a framework can't just work on the biggest things. It has to work on the absolute smallest. It has to bridge the divide that has stumped everyone for a century. General relativity and quantum mechanics.
The holy grail of physics.
What happens if we take this exact same Alena tensor framework and shrink it down to the quantum realm?
This is where it transitions from a fascinating cosmological tool to a potentially revolutionary unifying theory. Because the exact same equations used to describe the spinning kinetic structure of a galaxy can be applied directly to the quantum realm to describe quantum vortices.
Wait. You mean the mathematical equations governing a spiral galaxy 50,000 light years across are the exact same equations governing a subatomic particle?
Under this generalized framework, yes, the scale changes, but the fundamental geometric principles remain exactly the same.
That is incredible.
Specifically, in the quantum regime, the tensor highlights a profound coupling between spin and vorticity.
Let's define those terms, just to be clear. When we say spin in quantum mechanics, we aren't talking about a tiny particle physically spinning like a basketball, right?
Correct. Spin in the quantum realm is an intrinsic mathematical property of a particle, representing angular momentum.
And vorticity.
Vorticity is a measure of the local rotation, or swirl, within a fluid-like quantum field. Think of swirling eddies in a flowing river, but made of quantum probability amplitudes.
Okay, so the Alena tensor rigidly links this intrinsic spin with the swirl of the field. What is the physical result of that?
The result is a potential answer to arguably the most fundamental question in particle physics, the generation of mass.
Wow.
The math demonstrates that mass can emerge spontaneously as a direct result of the balance between the system's phase structure and this spin-vorticity coupling.
Spontaneously. I want to make sure I grasp the how here, because mass doesn't just appear out of nowhere. How does spin and swirl physically create the property of mass?
Think of it like this. Imagine trying to walk in a straight line across an empty town square. You walk effortlessly, right? No resistance.
Right.
Now imagine the square is filled with a dense crowd of people. and they are all moving together in a highly synchronized, complex circular dance. That's your quantum vortex.
Okay.
As you try to push your way through that swirling crowd, you encounter immense resistance. You have to constantly interact with the flow. In quantum field theory, the resistance a particle feels as it interacts with the fields around it is literally what we measure as mass.
Oh, man. That is an incredible visual.
The Alena tensor mathematically maps how the specific geometry of that spin-vorticity coupling creates that exact resistance. The mass emerges spontaneously from the geometry of the flow.
What makes this so astonishing is the parallel to the standard model. We are literally talking about the Higgs mechanism here.
Precisely.
The Higgs boson, the God particle that we spend billions to find at the Large Hadron Collider. The standard model says particles get mass by wading through the invisible molasses of the Higgs field.
And the Alena tensor arrives at the exact same destination, predicting how mass is generated but takes a totally different road.
It doesn't necessarily need a separate arbitrary field of molasses. It suggests mass could be generated by the internal architecture of the particle's own quantum field.
That's the profound implication. This spontaneous emergence yields direct mathematical analogs to the equations we already know from the Higgs mechanism and the Yukawa couplings that describe how the Higgs interacts with fermions.
It naturally reproduces it.
Yes, and it also naturally reproduces a known phenomenon called the Machoun effect.
The Machoun effect. Let's break that down.
It's a fascinating phenomenon where the macroscopic rotation of a system, like physically spinning a device directly and measurably, alters the phase of a quantum wave function.
So it links macro rotation to quantum behavior.
Explicitly. By reproducing this from first principles, the Alena tensor shows that rotation and quantum mechanics are deeply geometrically intertwined.
It's almost too perfect. Let's recap what we've covered.
Yeah.
A single mathematical framework that solves the dark matter missing mass problem by looking at kinetic angular momentum.
Right.
It solves the dark energy expansion problem by making it a geometric field invariant. And it solves quantum mass generation through spin vorticity coupling.
All under one umbrella.
It's basically suggesting the macro and the micro, the swirling galaxy and the subatomic particle, are fractal reflections of each other, operating on the exact same geometric truths. It is a stunningly beautiful idea.
It is very elegant.
But I have to force a reality check here. I have to play the skeptic.
Please do.
If this equation is so perfect and so unifying, why isn't it on the front page of every newspaper? Why hasn't the standard model been completely thrown out today?
Because science does not and must not advance based on elegance alone. Science advances by brutal, relentless replication.
And intense criticism.
Exactly. Failed attempts to break the model. Complex empirical comparisons. We have to recognize the absolute youth of this theory. The Alena tensor right now is only a 3-year-old research direction.
Which is nothing in physics time.
Connecting general relativity, continuum mechanics, and quantum phases is a massive achievement. But compare it to string theory.
Right. String theory has been the darling of theoretical physics for over 50 years. Tens of thousands of papers, hundreds of brilliant minds.
And even string theory still struggles to produce testable predictions. The Alena tensor is in its absolute infancy. It's the work of a single mind proposing a new path.
So there are massive hurdles ahead.
Daunting ones. It handles galactic rotation well, but can it explain the vastly more complex, chaotic gravitational lensing we see in massive galaxy clusters like the Bullet cluster?
Because clusters are incredibly messy, not neat spinning disks.
Exactly.
And what about the early universe? Dark matter is essential for explaining how matter clumped together quickly after the Big Bang. If you remove it, does the tensor provide a mechanism for early structure formation?
That's another critical test. Does it correctly predict the acoustic peaks in the cosmic microwave background? Can the quantum sector be developed into something truly predictive for the entire zoo of elementary particles? These questions will require years of work by independent teams.
It's a massive mountain to climb, and that actually brings up the architect of this mountain, Piotr Ogonowski. I was looking into his background, and it is fascinating, precisely because it's so unconventional.
He's not your typical cosmologist.
Not at all. He's not just some guy cloistered in an observatory. He's a lecturer at Kosmicki University in Warsaw. He's authored peer-reviewed papers in physics, yes, but also extensively in management and economics.
Yes, his background is highly applied.
He was selected as an expert to consult on changes for co-financing complex projects from EU funds in Poland, and even served in an expert group for the Chancellery of the Prime Minister of Poland.
It's a remarkably diverse resume.
Which makes me wonder, a researcher who bridges physics and complex management systems. someone who advised a government on how to allocate funds and manage logistical bottlenecks.
You're seeing the connection.
Right. Is it possible that his deep background in complex systems management and analyzing supply chains and dynamic flow is exactly what allowed him to look at the universe's dust model and realize it was a terrible static approximation?
It's highly likely.
Did he look at a spiral galaxy and see a dynamic supply chain of energy transport, while traditional physicists were just looking for a missing pile of heavy rocks?
What's fascinating here is that the history of science repeatedly shows us that interdisciplinary thinking catalyzes paradigm shifts.
Totally.
A physicist trained entirely in standard cosmology might spend their whole career trying to invent a new exotic particle to fit the anomaly, because that's what their training dictates.
But an outsider.
Someone who spends half their life thinking about how energy and resources flow through interconnected organizational systems might naturally look at a galaxy and say, you aren't accounting for the systemic transport of energy. The system is dynamic, not static.
It's the ultimate outsider advantage. Just apply it at the highest levels of tensor mathematics.
It is. However, we must continuously return to the foundational rule of the scientific method. Skepticism is a scientific duty.
Always.
Oganovsky acknowledges this himself. Until independent researchers, people with no stake in the theory, reproduce as fits, extend the tensor to galaxy clusters, and definitively test it against that inclination-dependent lensing we talked about.
It remains unproven.
It is a highly promising, mathematically beautiful, but unproven research tool, not yet a verified theory of everything.
But it is a massive structural crack in the foundation of the dark sector.
Unquestionably.
We've spent this hour pulling apart a truly dense, profound journey, starting with a universe dominated by untouchable phantoms.
Dark matter and dark energy.
And exploring how relying on that simplified dust model might have inadvertently forced us to invent those phantoms just to balance the equations.
And we've seen how the Alena Tensor offers a rigorous alternative. A universe where fluid-like kinetic flow and continuous transport generate the extra gravity we see.
Where dark energy isn't a hack, but a necessary geometric property of spacetime.
And where quantum mass beautifully mirrors the swirling mechanics of macro galaxies.
It replaces the dark, empty voids of the cosmos with this elegant mathematics of structure and spin. It demands we stop looking for missing puzzle pieces in the dark and realize the puzzle itself might be a completely different shape.
The physics community has spent decades searching the darkness. The Alena Tensor points us firmly back to the light, suggesting the visible structure and motion already hold the answers, if only we calculate the dynamics correctly.
Which leaves you, the listener, with a final, lingering thought to mull over. If the rigorous mathematics of the Alena Tensor ultimately prove true, it means the universe hasn't been maliciously hiding invisible particles from us in the dark spaces between the stars.
Right.
Instead, it means the most profound secrets of reality have been hiding in plain sight all along, written loudly in the beautiful swirling movement of everything around us. They were just waiting for us to invent the right language to read them.
It's a powerful thought.
It really makes you wonder, outside of theoretical physics, how many other seemingly unsolvable problems in our lives or in our world are entirely of our own making, just waiting for a fundamental change in perspective to suddenly make perfect sense.